Okay, good morning. So I see the room is almost full. It's time to start. One of those early sessions here. Well, it's good to have the room this full. So today, José and I will take you, to a new part of our journey in the storage world. In the previous years, we've been mainly here for SMB and in the Samba software specifically. So that part of our journey has not ended yet, but this is an entirely new topic for us since roughly a year ago. So about us? Oh, not about us. So even though it is very red in the slides and it covers the Red Hat logo, it's not a product pitch or anything. It's mostly about the upstream technologies involved in a new product we're doing. And we'll be mostly or almost exclusively touching the upstream thing. So it is our own view of the software here. Nothing that, we're not speaking for Red Hat. All right, about us. So yes, we've been in the open source software storage business since a while, contributing to a couple of projects. And as of recently, we are both part of the what we call container native storage team in Red Hat storage organization. So you will learn about what that actually means moving forward in the presentation. Anything you want to add here?
Not specific, not too much specifically, just we've concentrated our efforts in an upstream project called Gluster Kubernetes that you can find on GitHub, and we'll be touching over what components have gone into that repo and what that project is trying to do as the presentation goes on.
Right, exactly. So yeah, you will see a couple of open source projects that we're working on as part of this container native storage effort. And if you wish to put it like that, this Gluster Kubernetes repository or project is kind of the upstream phase of that technology. And it's kind of an umbrella project linking together a lot of these other projects that we'll cover as we move along. All right, so we are at the introduction. We'll provide some background. I mean, what's the situation? What are these container things in the first place? What is the storage problems that people are trying to solve? And what is our approach? Then we're going into the details. José will take you to all the details after I've laid the ground a little bit with the with this background. And we'll have demos along the way, and in the end, we'll have an outlook what we're up to for the next few months or 1 to 2 years maybe. All right. Okay, so this is like the super compressed version of what this is all about, the TLDR. So what we are having, we're talking about containers. I will be detailing a little bit on that in the guise of the Kubernetes orchestration system. So you usually have a cluster of nodes. And what it means when we're saying container native storage, it means that the storage, in our case, the Gluster software-defined storage system is actually running natively in the sense of inside the container system as containers, providing a very flexible way of giving persistent storage for the applications that are running inside Kubernetes. So we'll cover the details a lot more. So consuming whatever kind of storage is there, also we're going to go about what's happening here. Right. Oh, by the way, during the presentation, if there are any questions, feel free to speak up. Happy to take questions as we go along. All right. So that was the intro. It was like the totally condensed overview, and here is a little background. Okay. Containers. I mean, some people more traditionally viewed containers as very lightweight VMs. Nowadays, many people are speaking of containers, not looking at these so-called system containers, which abstract out the whole operating system with the init process and stuff like that, but as runtime isolations for individual programs or applications. This is the whole Docker and other software components paradigm here, basically. All right, so of course, so this gives you a nice abstraction. You can run hundreds and maybe thousands, sometimes containers on a single machine, be it a VM or be it a bare metal machine. That gives you the ability of run many such things without the additional stuff that you may even not need when you're running a certain application. They are, since it's basically starting a process with a certain isolation around it, in Linux usually implemented with these C groups, these kernel control groups, it is extremely fast. It just takes fractions of a second to bring it up usually, instead of starting a whole VM, which was the former way of abstracting out. It is ideal for what people like to call microservices architecture, which is instead of having one operating system running a lot of daemons that comprise a whole application on a higher level, you have multiple containers, and these containers talk to each other. So each component is basically its own container. If I were to think about my main Samba project, I mean, we have a couple of daemons that are running here. We have the Samba main daemon SMBD, we have WinBind, we have NMBD, we have the clustering agent CDDB. All of those in a microservice approach would run each in its own container and talk between the containers instead running all in one container. But for that project, I mean, we are not there yet. It's also maybe not for each and every project, but all these web applications, for instance, this is very standard. Web applications usually do it. They have this microservice architecture, one web head, one or multiple. They can scale independently. They have the database backend. All these servers are in different containers. So this is the microservice paradigm. And each component only needs to care about its own state. Basically, it's really very nicely isolated. Usually these components intercommunicate with RESTful APIs because, well, web protocols is basically what's always there and always available. Sorry for that. Right. So I was talking about Kubernetes. I was mentioning it. So, and it is, I said, oh, it's an orchestration system. So if you read on the website, it's an open source system for automating deployment, management, and scaling of containerized applications. I mean, in short, that's what people mean when they say orchestration. It is it's a cluster, as you've seen in the first graphic. It's like usually multiple nodes. And Kubernetes has the logic of scaling out an application over the various nodes in the cluster, making it, I mean, highly available and scaling out. The containers are managed in units they call pods. This is like the minimal unit you can deploy. It can become consisting of one or more containers that basically form a logical unit. And whenever you bring it up, all the containers will be brought up, and if you bring it down again, containers will be gone again. All of those in one pod. What you need, I mean, coming from traditional storage engineering, it took me some time to get the lingo, right? So when the programs in the Kubernetes world or applications are called apps. So this is not like mobile apps on a phone, but this is every program that runs in the container space. And the users of the software are called developers. This is, I mean, yes, because the typical user is like a web developer or something who's developing his applications. This is all about this kind of DevOps, roll out, bring down again, and stuff like that. So this is where it was originally most used. So remember, if you hear a Kubernetes guy talking about developers, it's the users. Okay. In principle, Kubernetes is agnostic, or it supports multiple container runtimes. We are using currently Docker, but you could use Rocket or Cryo, etc. And so one main thing here is that for your application, what does Kubernetes achieve? It entirely abstracts out the underlying platform, like hardware. It runs on-premise or in the cloud. It runs in bare metal and VMs. It runs on those cloud providers like Amazon Web Services, Google, Azure, whatever. Basically, you can run the Kubernetes operating system there, and then your application are completely abstracted away from the backend. So both the container runtime basically is for the individual instance, but the whole application by scaling is entirely moved away from that. So that is one of the biggest achievements for those kinds of applications. Now, what about storage, right? This paradigm is containers are entirely stateless. They have no state in the sense Usually what is done, you have this container image, you spawn the container, but everything that the container changes, I mean, writes into the file system is gone because you have like a memory, in-memory overlay file system on top of the image. So if you destroy the container, bring it up somewhere else, all the changes are lost. And this is intentional. But at some point, people realize, okay, some stuff should be persisted. Like, I mean, if I bring down the container, the changes that people may have done to the database are gone. So that doesn't work. And if I use local storage on one of the nodes, and then the application is brought up on another node, it doesn't know that storage. So you need some kind of storage that is available across the cluster nodes. This is the last point here. Storage must be able to follow the apps, right? So the content, the actual, for instance, web pages of a web application, the databases in the backend, also the configuration of your application, all that needs to be persisted. And interestingly, that came relatively late. I mean, sometime, I think early last year, the Kubernetes people basically started to implement what was then called persistent volumes. So the persistent storage infrastructure has been created in Kubernetes. It supports multiple access protocol more in the front end, so you can have SMB is in the Linux space not so important, but the NFS is one of the standard things to be used. Also, you can use block devices with iSCSI and then turn it into file systems, and I mean, or you can use other SAN block devices from whatever storage appliance. You can use local disks. You can use, in the cloud world, typically you have Amazon EBS disk, GCE persistent disk, Azure disk, whatever. These things are put into you can basically buy them and put them into your container hosts and can consume them there. So there's a variety of options with plugins inside Kubernetes to consume them. So that's all great. So why are we here in the first place, right? Problem is that this was just the start, and we observed that there is actually no one solution that provides all of these like high-level requirements. Storage should be highly available. It should allow for concurrent access, right? If you have these block devices, a SAN device, if you have a GCE disk, an ABS disk, they're just used there for exclusive access. You can't mount them on two nodes at the same time, or you risk data corruption. So what about like high availability and network resilience? Ease of scale and the flexibility also of consumption, right? You have a big chunk of block device for and abstraction of raw storage. They go in the same direction, right? If you have this big block device, you want to consume that flexibly, like, oh, I need 100 gigabytes here, I need 50 gigabytes there, or how do I consume that? How do I chop it up into usable units? Or do I have to request like 50 gigabyte GCE disk every time I need to give some storage to an application? That would be extremely it would make it expensive and also slow. The bigger these cloud disks get, the faster usually the guaranteed performance. So this is all about flexibility, scalability, and also this abstraction of raw storage. It's an important point, right? For each of these backends of raw storage, you'd have to create individual adapters, how to consume those. And remember, the Kubernetes thing is all about abstracting away the runtime from the application. But the storage is not abstracted, so you can easily move your, if you have one cloud provider, you still, through storage, have a lock-in. If you start with Amazon, it's difficult to transfer all the stuff. The runtime is easy. Applications could easily be scheduled on, for instance, Google. But the storage is locked. So this is what I mean with abstracting out. So, yeah, we thought, we have some, yes, please, a question.
Before you get into your real, money's like, can you go back one slide?
Sure.
And I apologize, I'm not very up on my containers yet. So, are you saying the front end is always the iSCSI NFS, and the back end is?
There are more of those. There are things where you can just consume a raw block device. The iSCSI could as well go down to the block storage, basically, right? You could have a local block device, format it, and put it into the containers. And then if you want to use that on a different node, basically if it's kind of SAN with iSCSI or real SAN or GCE disk, you can plug the disk into a different node when your application moves and bring it there. Yes, so these are like the only standard things that have already existed like a year ago in Kubernetes. Everybody's working more. I think there were Chef RBD adapters as well and stuff like that. So there's more than that. I just chose a few.
Yeah. Okay.
Right? Very typical standard. So the standard thing is people, yeah, let's use NFS. We have some block device, let's use NFS. So, and either NFS really inside, like starting NFS server on the node, which is bad because the node goes down, it's a cluster, you have to somehow make sure you bring up NFS on the other node, or you have something outside and consume NFS storage from the outside. That of course works, but some people, they don't, with a big, like, super big Kubernetes cluster for the applications, then maybe many people didn't want to have another software or hardware appliance outside for the storage. Why can't we manage all this stuff with Kubernetes, including the storage layer? This is one of the main things, right? And then have the benefit of abstracting out the back-end raw storage with that. So, yeah, I mean, you have seen the title. So we have Gluster, and with that, I'm handing over to José, I think, right?
Oh, sure. Alrighty, so good old GlusterFS that at least I've been working on for the past 5 years. It's an open source software-defined distributed file system. Its key feature that has been advertised since day one is that it's a scale-out file system, so that it's very easy to just expand your storage by just adding more Gluster nodes and adding more storage to each Gluster node. Gluster is highly available, is relatively easy to set up, especially with compared to some other high-end storage appliances out there. It's fairly easy to maintain. It's really flexible. The Gluster nodes don't have to be homogeneous, either in configuration or in storage availability. You can have different types of volumes within a single Gluster cluster, and each volume has a dizzying array of options that you can configure per volume and in some cases per cluster. Let's see what the key features that this has that makes it ideal for the Kubernetes world is how it being software-defined storage allows it to, as we mentioned earlier, abstract away the actual storage devices that it's consuming. You can just run a Gluster service on whatever node, tell it the devices that it's using, and then it can convert that into a multi-tenant volume that can be mounted from anywhere with network access. So then we figured, why not? And then when we were considering bringing Gluster into the world of Kubernetes, we thought, let's take it one step further. Why not put the entire storage service into containers? With the idea that this would fill the need for people who wanted to just have one method of managing their entire Kubernetes cluster, one method of managing all the resources that they're allocating within the Kubernetes structure. So having a containerized app for GlusterFS would allow you to use, what do they call it, control plane? Is that right? That's your favorite word, right? Yeah. Yeah, absolutely. Yeah, that allows you to have a single control plane to manage Gluster just like any other application, and it also allowed for some extension of existing GUI administration tools to monitor your storage as just another Kubernetes resource. So we figured, why not do that? All right, here's how we put it all together. Starting with the features of Kubernetes, as Michael mentioned, Kubernetes, as of early last year, implemented the notion of persistent volumes, where Kubernetes takes on the first step of trying to abstract away the actual storage from the apps running, so that apps only need to care about, I want X amount of storage with maybe these access methods. And then it doesn't care how that happens. It's up to the Kubernetes administrator to play the role of storage administrator by configuring storage and providing sets of persistent volumes that then applications can request. So the way this worked initially is that the administrator was responsible for creating whatever set of storage volumes they wanted to provide to their applications. So you would create an NFS export or multiple NFS exports, and then you would define persistent volumes to map to these NFS exports. Then a pod or a user would come in and create what's called a persistent volume claim, or PVC. Basically, that's the thing that says, I want storage of this size, and I want it either multi-tenant or single user, and a couple other storage features that you can specify. Nothing too granular. So then the PVCs are sent off, are taken by Kubernetes, and then Kubernetes takes care of finding a PV that matches the requested attributes from the PVC. And once such a volume is found, the persistent volume is then considered bound to the PVC. It then takes this now bound volume and presents it as local storage within the container. We'll get more into that a bit later. And then as of, I believe, September 2016, with Kubernetes 1.4, they allowed for both the static and dynamic creation of persistent volumes. And this is where things get interesting. So-called dynamic provisioning is basically storage on demand. With dynamic provisioning, when a PVC comes into Kubernetes, Kubernetes can then use a variety of what are called provisioners to create the volume without administrative intervention. So the way they implemented this is that a PVC mentions what it calls a particular storage class. A storage class is just a definition of a type of storage, and that part is written by the administrator. The examples that they usually give is that you can create a couple storage classes, like one called fast and one called slow. And then an app can request either fast storage or slow storage in its PVC, and then X amount of storage in either of those. And then you can specify whether, and then you usually specify that the fast storage is some sort of, iSCSI or NFS backed by SSDs, and then slow storage is something either, usually hard drives on a slower network link or maybe in another data center. So you create that storage class, and then the PVC mentions, and then the PVC mentions the storage class it wants to use. The storage class itself also defines the provisioner that it's going to be using. So in our case, for instance, you would have a storage class that specifies the Gluster provisioner, and then Kubernetes would invoke the provisioner to create the volume and then bind the persistent volume to the PVC. Anyone with questions thus far? We're getting into a lot of alphabet soup here. Right. So, the integration of Kubernetes with GlusterFS. There are a number of things that come together to make this all possible as container native storage, as we call it. Within Kubernetes itself, we've provided a Gluster provisioner and a GlusterFS mount plugin. I'll go into those in a second. We've provided a REST API in the form of Heketi, which is its own small standalone project that intends to be just a volume management interface for GlusterFS volumes. And this is because, Kubernetes being targeted for modern day web development, communicates between all its services with REST APIs. So it expects a REST API to talk to its storage. Then we bring in GlusterFS combined with Heketi. This allows you to have one or more Gluster clusters in operation for a given Kubernetes cluster. This was done to sort of coincide and expand upon Gluster's scale out feature. So one way easiest and most immediate way we could find to just bring Gluster into a world that just expects, huge, large and near instantaneous scaling was that you could just add additional clusters of Gluster nodes.
Just to chime in,
Yeah.
I mean, the scaling here refers to how many volumes are we able to serve from, not how many users simultaneously.
Right.
This is not the big challenge here, number of volumes. This is the challenge. If hundreds and thousands of apps want to have their own storage, this is the challenge.
Yes, the actual capacity of the volumes has been quite high for several years now, I believe. But the scaling to the point where hundreds or thousands of applications in a single Kubernetes cluster each may want their own special volume, that presented a bit of a challenge, which we worked around by simply adding additional clusters. Yes?
So what is the practical amount of PVs that you see per physical node, or per node within Kubernetes cluster?
Per node? That's not... Are you asking how many applications consume PVs per node?
Either.
Okay. Varies wildly, but it's not. People tend to think of it more as per cluster, because with containers being able to move around back and forth between nodes, there's credence is not given so much to what each individual node can do, but what the cluster can do as a whole. So per cluster, we easily see, at any given time, hundreds of volumes. And really one of the bigger challenges with storage in the container space is that Kubernetes expects the ability to be able to quickly migrate containers, and in fact does so relatively frequently, and in some cases will spin up way more temporary containers on an as-needed basis, and of course does scaling in a dynamic basis. So for all those, you need to be able to either mount or in some cases create additional storage very quickly, and that can be on the order of what are they doing? Again, if we go even further and say there are thousands of volumes available, you get in the hundreds per minute, or sometimes even like hundreds per second requests for mounting and creating volumes.
Maybe one additional thing about, how many volumes, etc. That's right. So how many volumes do exist is one thing. How many are really used at this moment? And then what is the frequency of create requests? And it varies widely also how beefy the applications are that you're running. If you have a lot of very, very small applications, you can run hundreds and thousands easily on a cluster. So we have seen various things from a few dozen to a couple of hundred per cluster to a few thousands. Recently, we had a project where the order of magnitudes of volumes is like they want to have a lot of 10,000s of volumes available and roughly 10,000 volumes used simultaneously. So that is kind of, and this is one of the challenges here really that Gluster was facing, because before that, nobody ever wanted to get that many volumes out of a single cluster, even or just a handful of clusters. So I'm going to touch on what we're doing about that a little bit later.
Right. And then just as another bullet point, since this has actually been a request that's come in as of late, especially for some larger users, they also want to be able to, in some sense, have their cake and eat it too, because they want dynamic container storage, but they also want to set up their own external specialized storage cluster, so that they don't have to put their storage where their compute is. So there's still that mentality going on. And Gluster in this case, Gluster and Heketi were designed so that you could do both, either or both. So Gluster can be standalone on its own hardware, and then Heketi will just be running, Heketi can be running anywhere. It can either be containerized or not containerized on one of the Gluster nodes or not. And this is in keeping with the flexibility we want to offer with GlusterFS. And then we've also written a small tool called GK Deploy, which helps automate a lot of the deployment or setup for this storage solution. So it is targeted at the containerized solution. It does support, it does currently support setting up external GlusterFS or using external GlusterFS clusters, but at the very least, the Heketi service must be containerized. If neither the Heketi service nor the Gluster services are containerized, then, well, we can't really help you much with that automation there. You have to set it up on your own. Alrighty. Now, GlusterFS dynamic provisioning in Kubernetes. As mentioned earlier, a user or developer, I guess, creates a PVC. The storage class or the administrator created storage class mentions the GlusterFS provisioner. That provisioner is extracted and invoked by Kubernetes. The provisioner then reads the data from the PVC to get the size and attributes of the volume that it should create. And then the provisioner via Heketi's REST interface tells Heketi to create a corresponding Gluster volume that matches these attributes. Heketi, in turn, since it can manage multiple Gluster clusters, first searches for a cluster that can fit these requests. If no cluster can be found, obviously, then we return an error. But if one is found, Heketi then executes the actual low-level Gluster commands to create the volume. And as mentioned earlier, Heketi tries to sort of, Heketi tries to sort of abstract away some of the nastier details of configuring storage. So it presents a higher level interface for things like how durable do you want your cluster to be, and what's the other one? It's durability, it's capacity, and.
But the main thing is, usually when you, as an admin, used to create a Gluster volume, you have to specify each and everything in detail about the type, and then you have to specify each and every disk, what we call bricks, that kind of build up the volume. All that stuff is done by Heketi. You just, in the easiest case, you just give a size. Give me 100 gigabyte volume and figure out the rest yourself, and that's the main thing.
Yeah. So in that sense, Heketi takes care of. All right, I found this cluster that has a capacity to serve 100 gigabyte volumes. 100 gigabyte volume. I will then create the underlying, Heketi then implements the storage by creating 3, for instance, 100 gigabyte pools of storage. We call them bricks. It does this using LVM, and then creates those bricks, puts them together into a Gluster volume. All this would be things that you'd have to specify individually, as you mentioned, on the Gluster command line. But Heketi just kind of makes some assumptions about best practices that have come up in the community over the years, and just applies those just imposes those onto the Gluster volume. So, for instance, this has the consequence that a Heketi managed Gluster cluster must have at minimum 3 nodes, because Heketi expects to do a minimum 3-way replication of all data on each Gluster volume. So it needs at least 3 bricks to do this data replication. Yep. The GlusterFS mount plugin. Kubernetes has a variety of plugins shipping with it that allow it to mount various types of volumes. In this case, and then once it takes those volumes and mounts them on the host, on the actual Kubernetes host that is running, and then bind mounts that mounted storage into the containers to present it as local storage. The GlusterFS mount plugin was written to ship with Kubernetes, so it's in the Kubernetes source tree, and thus requires that the Kubernetes host, if you want to use Gluster volumes, must have access to the mount.glusterfs volume, or mount.glusterfs command. Heketi, as mentioned earlier, hides the nitty-gritty details, just takes size and durability types. It recognizes various commands like create, delete, expand, etc. And also has a companion tool called Heketi CLI. The Heketi CLI is particularly useful if you don't want to use dynamic provisioning for a given volume. You can use the CLI to manually create a particular Gluster volume. And then if you download the slides, you can get the GitHub URL. All right, and then the final step was containerizing all these services. In the case of Heketi, that was a simple use case. Heketi is just a single service, and given that the Kubernetes model is targeted towards running single processes inside isolated runtimes, this was fairly simple to do. It's written in Golang, so all you really needed was a container that could run the binary, and you're ready to go. Heketi also maintains a database of some volume metadata, which needs some persistent storage. And currently our default solution is to create a Gluster volume on its managed cluster to store the Heketi database on. And then it just mounts that Gluster volume to read the database. The Gluster container was a bit more complicated because Gluster has some dependencies on other processes running on the same system. So, for instance, you need it expects RPC bind to be running on the system, and the way it handles that is that it attaches to the host network. So it basically assumes the network identity of the host that it's running on. Docker has a feature that it calls host networking, and that just basically allows the container to straight up take, in particular network ports on the host. Typically, if you want to allow a container to be accessed via a port on the host, you have to manually map the port from the host into the container. Whereas if you just use host networking, you have direct access to the ports on the host. And it runs as a privileged container, which means it can do certain things that containers are not normally allowed to do. So for instance, in this case, it can be given direct access to the /dev directory on the host that it's running on. And that's how it gets access to the block devices that Heketi then uses to create logical volumes on and turn them into bricks. And then it also uses the privilege mode to bind mount certain directories on the host, and that's where Gluster stores its state. It stores it in varlib, GlusterFS, and a couple other places on the host itself, so that the actual service that's running doesn't entirely care what node it's on. It just reads the configuration and then assumes the identity of that node. All right, and now a brief demo.
No,
if we have time for that.
don't escape. I'm just like that. Yeah, I'm starting it for you. So, you go.
All right, so here's a quick demo of how relatively easy dynamic provisioning works. And because we are Linux geeks, this is all, of course, on the command line. So here's the current state of the Kubernetes cluster. We have 4 nodes and a couple Gluster pods and Heketi running. Here is a storage class definition with the name my storage class. We specify the Heketi.
It doesn't work.
Oh dear, what is that?
That's crap. Wow.
Yeah, what did you do?
I don't know. No. Yeah, maybe wrong screen size. Maybe it doesn't work. Yeah. Crap. No, that's not the W. That's not the weight stuff. Sorry for that. So we
probably is the wrong screen size. Are you currently online?
The question mark in the upper right corner tells me no.
Nope. All right.
That's very bad.
Yeah.
These are your control sequences.
Oops. Oh well.
Well, yeah.
Let's see if it'll do it again.
Damn. Yeah, it'll do it again, I'm sure.
Yep. All right.
Anyways.
All right, we've hit a limitation with ASCII Cinema. All right.
That's okay. When we exit the editor, it should be better again.
Yeah. Here's open.
So the main point was you don't see it anymore. It was this mentioning of the storage class, which is GlusterFS.
Okay, good.
Yeah.
And then you just run a command to create the storage class. There it is. And now when you look at the PVC YAML.
Ah, crap. You can just space to pause it, I think. Yeah. No, it's
Nope.
gone. That's gone. Yeah, it does. Oh, no, it doesn't.
Still keeps going. So
Beautiful.
You saw
Isn't that
yes.
nice?
Yeah, lovely.
10 minutes right now. Yeah.
Lovely.
So-
All right, so you execute another command to create the PVC. And then you see that it is currently in pending state. It is looking for a PV to bind to. You wait a couple seconds and it's bound to a PV that was dynamically created. You can see that it's got a capacity of 2 gigabytes and it's got an access mode RWX. We're not sure why X, but it stands for read write many, so that multiple users can access it at once. Right? Isn't that so intuitive?
Yeah. Instead of RWO, which is read write once, that's more intuitive, actually.
Yeah. Here we go.
There's the application, right? The application container.
Yeah, there's no way to pause this
No.
thing.
Yeah, so the thing is, well, in the end, there were more links. So the Gluster Kubernetes repository has all the demos. You can click there. You can just watch them online. It's been prepared. So I'm sorry for that. Really bad preparation. Okay. So here's basically we are showing we intended to show the actual description of the application, how it consumes the persistent volume that the user previously has requested to create. And now the application.
So then now the application pod is creating. We wait a couple seconds and it's now running.
Yeah.
So then, right.
So it's a web service. It's an Nginx container.
So then we write some data into the Nginx. We curl it and we get the index HTML we expect. So now we exec, as they say, into the container. So now we're actually running a shell within, we're running a shell within the container, and we saw the mount points that were currently being used. So then we just cat this giant string
Beautiful, isn't it?
to where the file is located, and we see that the data has actually made it onto the storage within the container.
I think that's it. Yeah, up. Mm-hmm.
Yep.
Right. So, sorry for this messed up demo, but you could see what is the basic idea. Yes, that's a question.
One question I was trying to understand the stack you have. So you have Gluster volumes which are mounted on this node, and then the data protection is done using LVM, and then you create a file system on it, which is then mounted into the.
Not quite.
Not quite. You create the LVM, and then you put a file system on it. That file system, we call it a brick. And then Gluster takes a number of bricks, in this case a minimum of 3, and then puts those together into another sort of logical volume. So Gluster presents a single file system, whereas underneath what's happening is that a given file that you see could actually have multiple copies, is replicated across the 3 file systems underneath. But you still only get a view of one, and it's that single volume that is then mounted onto the host.
So maybe the confusion is Gluster doesn't consume block storage. Gluster consumes file systems.
Yes.
No, really data protection. We could use just local disks, format them, and use them, or directories in them. But here we choose to use LVM because that's how we implement snapshots. So it is the protection is rather done by user or group IDs on the host, etc. If you mean by protection that I've requested the storage and no other user should have access to it.
Oh, the HA.
Oh, that's high level. You have on each node, assume you have a 3-way replica. That's pure Gluster. There's nothing to do with Kubernetes, right? That's before. So you have 3 nodes. A local disk on each node, you create a file system, let's say with LVM on the block device, etc., and each same size file system usually, and Gluster puts that together into a replicated volume. So as long, your node can go down, you still have the access to the data, right? Does that answer the question?
So data protection is on the Gluster level, not LVM.
Right. And just mentioning what we've just seen here with the dynamic provisioning, right? Or we kind of almost succeeded to see is here you see the abstraction of the underlying backend storage, right? Gluster consumes just something /dev/ whatever disk device. This could be a GCE disk, that could be a local disk, that could be a SAN, and so from there, it will be exactly the same whether you deploy on-premise, in GCE, in Amazon, etc. So you just have to set up the Gluster and give it the raw block devices. Afterwards, you don't need to care about these block devices or treat them anymore. That's actually the nice thing about it. So similar like Kubernetes and the Docker runtime, abstract out the runtime environment of your application itself. This abstracts out the storage and makes it really convenient. You're requesting like a few terabytes of GCE disk on all your nodes, attach it, and Gluster will take care of chopping it up upon request into like small chunks, like a gigabyte. Many people just need a little bit, like even a few hundred megabytes would be sufficient. Requesting that from Google or Amazon is actually very expensive. Also, you have a limit of a number of how many volumes you can attach to a node and stuff. So this is completely getting rid of these limitations. So that's the beauty. So just very briefly about the roadmap. So dynamic provisioning, as was mentioned, was added over Kubernetes 1.4 last autumn. And Gluster was one of the first and still is one of the main implementers of that feature because that's the flexibility we can offer. Also, not many of the backends allow, if you use them directly, this what we saw RWX, right? This shared access, multiple containers on multiple nodes accessing the same thing. NFS can do that, of course, but it has other issues for our purposes. So in 1.5, we added improved the numbers, scalability numbers. We had so these what we call day 2 operations. Hey, what happens if a disk goes bad? If you need to replace it after it has failed, something like that. So currently preparing for later this month a release that's based on Kubernetes 1.6, improved read-write-1 support with Gluster block. So we are getting some kind of iSCSI-backed block storage access. That is intended really only for read-write-1's volumes. That is more of a performance side, better suited for stuff like databases that are heavy on metadata operations, which the distributed file system is really by its nature not very good at. Support logging like Elasticsearch stored on Gluster. Still improving scalability with what we call, I misspelled it, brick multiplexing in Gluster. And we also have support for removing a node and experimental S3 object access, because some of those web applications, they just like to use S3 access to objects. So this is what's going right now and will be released soon. And in the future, there's a lot of stuff that we are planning on. Many of the things that Hekedi and Gluster can do are not yet integrated into Kubernetes primitives because Kubernetes doesn't have it yet. But we are working on snapshotting in Kubernetes, so we are actively working with the Kubernetes community to get that forward. Geo-replication for synchronizing data between two clusters is possible with Gluster, but Kubernetes doesn't know about it. There is a question by Jeremy.
Uh-oh.
So I noticed that you put the Hekedi database on Gluster volume.
There's one option, yes.
Yes. Isn't that a bit of a bottleneck that you can't do massive amounts of provisioning?
Yeah, that is indeed. It is, yes, it's very horrible. It is one of our problems, but this is how it was solved initially. Yeah, putting it in etcd as well. So
BoltDB. It uses BoltDB.
Which is, I think, what is also backing etcd at point. So it's supposed to be very fast.
I think it's a NoSQL thing.
It's like, it's a record p-value database like GDB, but in Golang. So if these projects, most of these are in Golang, like Kubernetes and Hekedi. So, but we are working here on the, so the question was, I didn't repeat, sorry, I keep forgetting. That's a bad idea to have Hekedi database on the Gluster volume. But what we did this year, what we do in the future is, we are planning to reconcile the Hekedi software with Gluster proper to bring that logic that was originally intended for Gluster proper, but we need to get started, put it back into Gluster proper, and then there will also be not this problem that we have two layers of state, Gluster knowledge and Hekedi knowledge. If we have a Hekedi managed cluster, better not fiddle with the volumes on the low level. So this is also going to be solved in what we call brownfield. So we can add, there's an existing Gluster cluster, we can then do it with that. So
And it should be noted, a lot of these more advanced features that are listed at the top, you can currently take advantage of them even in Kubernetes. You just have to, of course, do good old-fashioned manual storage administration to actually get them to work underneath. But we're trying to get that into Kubernetes and have Gluster be one of the first ones to actually take advantage of that.
And one thing, volume expansion, for instance, has just landed. So in the 1.7 area, we will be able to do, the user will be able to request expanding his volume by just doing it the Kubernetes way. So there's more stuff to come. For instance, the lower things here use local block PVs when ready, and in Kubernetes, and stateful set for Gluster containers to remove a little bit the very special nature of these privileged and highly, let's say, non-microservice containers, to be a little more better able to scale them or treat them with Kubernetes primitives. So this is all that is gonna happen. I think we have consumed our time, and we had a lot of questions already. We're basically running out, right?
You can take a little bit of time for questions.
Good.
We have a coffee break now anyway, so we can actually have a little bit of time.
Right. So time's up. We had a lot of questions, but since that's a break, I'm happy to accept more questions.
But first, thank you very much.
Yeah.
All right, now, questions.
Right.
So,
Yes.
do you ensure that every week lands on different host?
So the question is, do we ensure that every brick lands on different hosts? Yes. So Heketi has this kind of, this is what Heketi does, right? It makes sure that each brick, each replication entity ends in a different failure domain. At minimum, this is different hosts, but we can also add zones to our topology input file, which we say, okay, I have maybe several racks, or I have even data centers, and I can add zones to the topology to make sure that, for instance, each replica set has one disk on each data center or rack or whatever. That can be done, yes. Well, there was one question back there, and then over here.
Okay, so this presentation was all about integration with Kubernetes, which I understand with OpenShift, with Redshift, what's stored with Mesos and with Docker, volume orchestration, and maybe a step further to CSI.
Nothing as of yet.
So question, what is the relationship? I mean, talking about Kubernetes, there are other runtimes, there are other orchestration.
With the Docker volume drivers, with the container storage initiative, with
Yeah.
with
So
I believe at the moment we are keeping track of those discussions. There's no hard set plans as to where to go with them, but we're definitely keeping track of the discussions. We have regular. We make sure to regularly talk about these things and keep an eye on where things are going in the future. The amount of development effort currently going into just keeping up with Kubernetes is enough, and of course, Red Hat strategy with OpenShift, etc.
okay, one thing, I think Kubernetes is currently talking about moving to Cryo instead of Docker. So of course, we're doing everything. We are working with Kubernetes most tightly. And it was mentioned OpenShift. We didn't explain that. If you hear OpenShift, this is basically Red Hat's distribution of Kubernetes. There's an upstream of that. This is called OpenShift Origin. This is basically taking Kubernetes, adding a little bit, just like Linux distributions add stuff on top of the Linux kernel. We add some stuff onto it, like little security and convenience around it, an installer, stuff like that. So OpenShift is more or less to be taken synonymous with Kubernetes for our purposes, just a Red Hat product around it. And we are not looking at other like Mesos currently. Kubernetes is the thing we're using, but that might change. And for instance, we are currently talking to the CNCF for this project. But also there's like the Rook project, which has been going in via Ceph deployment into containers. They're now also discussing with us about Gluster. So everything, this is a very, very, everything is much in flux currently, but currently we're focusing on Kubernetes and Docker. So
it should be mentioned that the upstream Kubernetes, upstream Gluster community is of course fairly Red Hat centric. So if you have, but if you have like one or more developers that are interested in bringing Gluster into other platforms, please feel free to join.
But the only thing where we're specific for Docker is that we have these Docker containers. The Kubernetes specific things, they could change when we have a container for a different runtime. Sure, that wouldn't prevent Heketi and other stuff from working.
Right, up here.
There was another question over there. The question is, for the replication in Gluster, what kind of read-write consistencies do we have? We have the consistencies that when the, it's really, fully POSIX file system, when we write and the write call returns, basically it is on disk. Or, whatever the Linux system, cache, write through, whatever. So it is really implementing the POSIX, read, write, whatever calls. Does that answer the question? Yeah. Well, yes, we do have strong consistency. The question is, in multiple data centers, we only support that if the latency is very low, like almost like rack-to-rack data center. It's not like WAN kind of connections. For that, we have this geo-replication. You have to set up 2 clusters, and you have a master and slave, and you sync the stuff over. But that is just in the process of being integrated with Kubernetes. So currently, it's cluster only, at least for there are beginnings. Yeah. Another yes, no. Okay, over there, and then I don't know who was first. I don't know. Maybe back and then here at the front.
I just got a comment real quick on the last question. As far as converting what you guys are working on to Docker, you basically do 2 things pretty light, and both of them are very lightweight. First would be basically a compose file to write a Docker stack for your container for your containers to run in a Docker Swarm environment, and then a little shim for a Docker volume plugin to run packaging. It would probably, for somebody who's familiar with the project, about a week's worth of work, maybe less.
Cool, thank you. So the comment was that there's not much work needed to bring the Gluster Docker container into Docker Swarm, for instance. Yeah. It's just a matter of writing, 2 files?
Yeah, basically. Well, one service for the plugin, and then a compose file.
A service for the plugin and a compose file, and it would take probably a developer familiar with Swarm about a week to do it.
Well, we also, this is also why we're trying, despite influences from the Kubernetes community, for instance, to put most of the logic into Hikedi cluster proper, so that when at some point the orchestration or runtime changes, we have to do little changes. So some people try to put all the logic into Kubernetes. We're trying not to. In this case, so maybe very, very thin layer in Kubernetes and all logic in Hikedi cluster. So there was another question.
So you talked a lot about dynamic creation. Once that volume is created by one container, how does that container re-access it later, or how does another container node pick up that access later?
So it's all tied to the PVC. As long as the PVC exists, that volume exists. So the container goes down, the PVC is still there. The container specification that you saw very briefly and then scrolled away mentions the PVC itself. So any new container that comes up mentions that PVC, gets that PVC, and then once the user/developer deletes the PVC, then the provisioner takes care of removing the volume in the back end.
Depending on the policy, even you can have
Depending
it stick
on policy,
around
yes.
or be recycled or whatever. This is Kubernetes allows a lot of things. Currently, we only delete it and make the storage recyclable forever.
It should be noted on that point, Kubernetes technically allows for multiple end-of-life policies, but currently Kubernetes in general only promotes delete because of the complications involved in the other retention policies. Anyone else? Nope. All right, let's go get coffee.
Yeah,
Thank you very
again.
much.